All right, so this begins a unit of waves. We're going to be talking about mainly about the types of waves that you'll see in real life over the course of this unit, right? So this unit is probably going to take 2 weeks, similar to similar to the what's the last unit we did? Oh yeah, circuits, similar to circuits. We're going to cover magnetic fields sometime later, and probably elevators as well. So those are two topics that I haven't covered with you guys yet, that I mainly skipped over. I skipped elevators when I was talking about force, and I skipped magnetic fields when I was talking about circuits. And magnetic fields are very important to circuits, but we'll talk about it later. So let's actually focus on waves. And when I say waves, I don't really just mean like water waves, like the wave you do with your hands or what happens with water, right? I don't mean that. I mean, well, they include water waves, but there's more to it, right? There's more to it. We're going to start simple. We're going to start with a pulse here, right? So if you ever watch medical dramas, right, you see a line, and we call this the equilibrium line, right? Because it's in the middle, and it doesn't change. And then as you see this pulse as it goes, you see it going down and then up and then down and up. And so it deviates from the equilibrium line. It deviates from the middle line, right? So represents a type of wave. It's called a pulse, right? We call it a pulse, right? And a pulse or wave is a disturbance in the medium. Well, what is a medium, right? What the hell is a medium? Medium is anything that something travels through. So let me give you an example, right? So this is a pulse, right? So you see a pulse, you see the wave traveling through it when I push this rod up, right? So there's a disturbance in the medium. The medium is the rope, whatever the wave is traveling through, whatever this thing is. It's like a line of particles, I'm assuming, right? So that's and what was the and so this is a pulse, right? And this pulse. There's also something here that's very important to notice, and I'll talk about what you should notice later, but we'll continue on, right? So the medium is anything that the wave or the pulse is traveling through. And in the case of the FET simulation, and in the case here, it's the rope or the particles, right? Let's actually. Uh, so now we talk about parts of a wave, right? We kind of know what a wave is now, kind of, but now we want to know what the parts of a wave are. All right, so you've maybe seen this in math, right? You've maybe seen this in math. This is called a sinusoidal wave, or in other words, it's a sine wave, right? It's a sine wave. So you see it starting at zero, going up and then down, and going up and then down. So there are two vocabulary words. Well, there are four rather, but there are only two vocabulary words I want you to focus here, right? I want you to focus on the word amplitude, and I want you to focus on the word wavelength, right? And the wavelength is represented by the symbol lambda, right? This curved, like upside down Y. We call that lambda. And this is represented by the word A, which is amplitude. And so your amplitude is how high or how much energy. Well, for now, let's say how high it goes, right? So how high this wave goes, that's your amplitude, right? How high the wave goes is your amplitude. And wavelength is another very important concept. A wavelength is just one cycle of a wave, right? And the way they depict a wavelength, there are two ways to think of wavelength, right? The thing of seeing it is, well, the first way is you can think of it as this red line right here, right? So I drew this red line on this picture, and so you see this red line starting over here, right? It starts at zero, the equilibrium line. We call this line in the middle the equilibrium line. This line. So it starts at zero, goes up, and then down further, and then back up. And so that is one cycle of a wave. That is one cycle. That is one wave. Well, that is the wavelength of this wave. The wavelength of this wave is one cycle of this wave. So there's a up part, right? There's an up part, and then there's a down part. It doesn't matter where you start, as long as it's this length, that is your wavelength of the wave. Let's look at this one right here. Let's look at this top one. It says that the wavelength, if you start from the top of this wave and go all the way to this wave right here, that's also one wavelength. And that does still make sense, because the wavelength of one wave is just the length of one cycle. If I measure 1 meter, if I measure 1 meter in my living room, it's still gonna be 1 meter in my kitchen. There's also still gonna be another meter. So no matter where you put a meter stick, for example, right? No matter where you put a ruler, wherever the ruler is, it's still gonna be measured the same exact thing. Because let's look at this. Let's look at this. So let's actually. I think it's easier for me to just copy paste all these things right here. Actually, this is perfect. I should have thought of this before beginning this recording. So the wavelength is one cycle wave. So it starts here, and that's the simplest way you can think of it. But if I take this arrow and I implant it right here, well, that's still one wavelength. You still have a wavelength of a wave. If I put your wavelength down here, it's still one wavelength. So no matter where you put this length, it is still measuring one wavelength of a wave, right? It is still measuring a wavelength of a wave. And that's how you can think about it. And it's fine if you don't get it immediately. I would just look at this picture, maybe internalize it a bit, right? We'll talk about crest and trough later, right? That's how you pronounce it. And so this is just another example of waves, right? So you have a wave-like motion, and you have the thing, well, waves being generated. So I'm still gonna skip over crest and trough. Hold on. Yeah, I'm still gonna skip over crest and trough for now. I want to talk about the equilibrium position, right? So your amplitude is how high, it, how far away it is from your equilibrium position, right? That's how far away it is. And so your wavelength is again one wave cycle, and your wave cycle, your wavelength, as long as it's measuring one wave cycle, it can be drawn from anywhere. It can be drawn from anywhere. Now, let's take a look at the first type of wave, and it's called transverse wave. Okay, this is called a transverse wave. Now, your transverse wave, you'll see a GIF of the image, the how it moves in this GIF right here. Okay, so this part goes up, which coincides with the wave going up and then down and going back up and then down and going back up. And so the highest part, we're gonna call that the crest, right? So the highest part that it goes, we call that the crest. And so the lowest part that it goes, we call that the trough. All right, we call the part where it goes lowest the trough. Again, you see the wavelength and you see the amplitude because the equilibrium position is in the middle. The equilibrium position is in the middle, and the amplitude is how far you are from the equilibrium position. Okay? All right. Now, there's something really, really important that you have to figure out here. And it's that transverse waves. Hold on. I'll talk about that later. Yeah. So this is a transverse wave. Okay, this is a transverse wave. And so now another type of wave, we call it the longitudinal wave. And longitudinal waves behave differently, right? As you can see, a transverse wave, the particles move up and then down and then up and then down and then up and down. Right? The particles move up and down, up and down, up and down. Uh, but in longitudinal waves, the particles don't move up and down. They just move left to right, left to right, left to right, left to right. And so that is the one big difference between transverse waves and longitudinal waves. That's one of the things you should remember is that transverse waves go up and down while longitudinal waves go left and right. And so, what does compression, instead of saying crest and trough, right? So, we used to say for transverse waves, we say that crest is the top part and the trough is the bottom, the bottommost point. We're going to call the top part compression and the bottom part rarefaction. Why do we call it compression rarefaction? If you take a look at this, right? The waves, as the wave travels, you see that the particles are compressing. They're compressing and then they're expanding. They're compressing and then they're expanding. So if you follow this image here, if you follow this right here, you see that compression and rarefaction as it goes on. Right, so it's compressing, then spreading apart, compressing and then spreading apart. Now, there's a big question you need to answer here. Do the particles go any significant distance along this wave? I want you to focus on the particle here. Right? If you look at the particle here, the particle is not traveling any significant distance. The particle is staying in a set area, right? It's just moving back and forth, back and forth. The particle doesn't travel with the wave, right? The particle doesn't travel with the wave. It doesn't travel with the wave. The wave travels, but the particles don't move. And so this is the biggest misconception students have, right? This is the biggest misconception students have. Is that they think that waves travel, that waves move things. That waves move things. They don't. The wave causes a disturbance in the medium, right? The medium moves, but nothing moves along that medium. The particles move back and forth. The particles might move up and down, right? The particles themselves might move up and down or left and right, but they don't actually travel with the wave. Right? And that's the biggest thing you must notice, right? That's the biggest thing you must know. So, what do waves actually transfer? They definitely don't transfer particles. Waves definitely do not transfer particles. Waves transfer energy. Okay, waves transfer energy. And so, let me see if I have a. Yeah, so waves only transfer energy. So, what type of wave is a sound wave? Right, what type of wave is a sound wave? So if you focus on each individual particle, you'll see that there's a compression, right? There's a compression and a rarefaction. So you see these compression areas and the rarefaction areas. Again, the compression areas are, right, expanding and compressing, expanding, compressing. And so, and if you take a look at these particles, again, these particles don't move anywhere. These particles don't actually move anywhere, but there is so is a longitudinal wave because the particles are moving back and forth, right? And we know that since we see a compression and a rarefaction, we know that a sound wave is a longitudinal wave, okay? So a sound wave is a longitudinal wave. It's a longitudinal wave. So what is so waves never transfer matter, right? Waves never transfer matter. This is just really just a review at this point. I just wanted to summarize. Waves never transfer matter. They only transfer energy. Okay, waves never transfer matter. They only transfer energy. Right? So an amplitude measures greater energy transfer. So the higher you go, let me get it. So let's actually transfer this over here. The higher you go, right, the higher your amplitude, the greater your energy. Actually, let's go back to your PhET simulation. Let's go back to your PhET simulation now. So let's make it oscillate. Let's actually, so your amplitude is 0.5, right? And so if you increase your amplitude, you're increasing your energy transfer. All right, you're increasing your energy transfer if you increase your amplitude. And so let's decrease it now. And so your amplitude, again, zero amplitude, high amplitude, medium amplitude. And so again, you're equating amplitude to energy. Okay? You're equating amplitude to energy. And that's all about the difference between transverse and longitudinal waves. Let's look at the motion of the particles. So particles in transverse waves, they move perpendicular to the direction of the wave. Okay, direction of the wave. So they go up and down. So if the wave is moving this way, right? If the wave is moving to the right, if the wave is moving to the right, then the particles in your waves move perpendicular. They go up and down. So we describe the direction as perpendicular to the direction of the wave. And longitudinal waves, you see that as the wave moves to the right, you see that the particle just moves back and forth, back and forth. And so then you can say that particles in longitudinal waves, they've moved parallel to the direction of the wave. Okay, so particles in longitudinal waves move parallel, while particles in transverse waves, they move perpendicular. So parallel, perpendicular, parallel, perpendicular. Okay, and so a water wave is actually a combination of a transverse and perpendicular wave, right? This is a combination. And the orange dot highlights the particle. So not only does the particle move up and down, it actually moves left and right as well. So a wave is both. A wave is both. It's a combination of both. Now, this is also a common question on your regions. Uh, your regions questions, and also in the Google form that is attached to this homework. Where will the particle be next as this wave propagates? Right, so let's take a look at the first image. Let's take a look at the first image. So where will this red particle be as this wave moves to the right? And so there's an easy way to think about it, right? There's an easy way to think about it. As your wave moves, if your wave is moving to the right, well, all you have to do is you have to just take a look at the wave, the line of the wave to the left of this particle, right? So if this wave is moving to the right, look at the left side of the particle. And you see that this line right here, well, that's where it will be next, right? That's where this red particle will be next. And so I draw it, or or you see it rather here. So as this wave moves to the right, the next location of the particle is gonna be uh the line near the line on the left. And so if you go down here, that's where it's gonna be. And as this wave goes to the right, it's gonna continue along the path on the left, right? So The left side of this particle depicts where it will be in the future. So as you go along here, as you keep going down, as this wave keeps going to the right, as this wave keeps going to the right, you will see that the red dot follows this path. And if you look closely at this GIF, that's what it is also saying. So I would maybe pause this video or take a look at this PowerPoint to fully figure out what is happening here, to fully figure out, well, where will the next location of my particle be? Because this is this might take a while for you to internalize, right? This might take a while for you to figure out, well, to predict where the particle will be, to make sense of what I'm saying here. So I would take a look at the PowerPoint or would study these images more or this GIF more. All right. Let's actually talk about the uh, let's actually talk about this now. So your Google form, the questions on your Google form, let's actually make this larger. Your questions on this Google form, no, there are no math questions here. All right, they're entirely conceptual, and because they're entirely conceptual, and they don't really require a lot of thinking, um, or rather much time. There are 15 of them, but I do expect you, if you do, I would maybe I made them because I thought it would take you guys like 1 to 2 minutes on each question, right? So 1 minute for each question, 15 minutes. So 15 minutes is pretty manageable. Or 1.5 minutes. 1.5 minutes times 15, that's like 22.5 minutes. So 22.5 minutes is also manageable. So number one, a student generates water waves in a pool of water, right? You can kind of think of it like this, right? So you're generating water waves. So in order to increase the energy carried by waves, the student should generate waves with a what? Right? You want, and again, you know that energy is related to amplitude. Okay? So the higher your wave is, the greater your energy, and that means you need a higher amplitude. So again, energy is your amplitude, right? Energy is represented by amplitude. You guys can answer this one. We talked about this in the video. This should be simple. So this transverse wave is moving to the right. Point X represents a particle of uniform medium. Which diagram represents the direction of motion of particle X at the instant shown? So if the direction of wave, we talked about this at the end of the PowerPoint, at the end of the lesson, if your wave moves to the right, right, if your wave moves to the right, then the left side of your particle predicts where it will be, right? The left side of the particle predicts where you will be. If your direction of the wave is moving to the right, left side of the particle predicts where it will be. So since the direction of the wave is moving to the right, and the left side says that it's going to go up, it's higher, that means this particle in the future will go up, right? It's going to go up. And so option 3 is the correct answer. Use the same logic for this question, except this question, you're actually just moving to the left, right? So be careful with that. You're moving to the left. Same type of question, and this question moving to the right. We talked about this as transverse waves as transverse wave travels through a medium. The individual particles of the medium move what? Talked about this. Maybe take a look at the PowerPoint. I would just read the question here. That seems doable. This is doable. It's a longitudinal wave, so how do longitudinal waves move? Uh, this should be easy. It's a longitudinal wave, longitudinal wave, longitudinal wave, longitudinal wave. Easy. We talked about this as well. All right. All these questions should be fine. If you have any questions, just give me a comment and I'll help you. But they should be fine overall.